As with propositional resolution, Herbrand resolution works only on expressions in clausal form. Fortunately, it's possible to convert any set of Herbrand logic sentences into an equi-satisfiable set of expressions in clausal form. The definitions here are analogous to those for propositional resolution. A literal is either a relational sentence or a negation of a relational sentence. A clausal sentence is either a literal or a disjunction of literals. And a clause is a set of literals, and as in propositional logic, represents a disjunction of the literals in the set. As with propositional clausal form, the empty set is also a clause. It's equivalent to the empty disjunction and therefore is unsatisfiable. The procedure for converting relational sentences to clausal form is similar to that for propositional logic. It goes by the catchy name of INCIDO, which is an acronym for the steps of the procedure. Some of the rules are the same as those for propositional logic. However, there are a few additional rules to deal with variables and quantifiers. In the first step, implications out, we eliminate all occurrences of the implication and biconditional operators by substituting equivalent sentences involving only and, or, and not. In the second step, negations in, negations are distributed over other logical operators and quantifiers until each operator applies to a single atomic sentence. The replacement rules shown here do the job. We eliminate double negations. We use De Morgan's laws to distribute negations over conjunctions and disjunctions. And we distribute negations over quantifiers. When this step is done, any remaining negations are applied directly to atomic sentences. In the third step, standardize variables, we rename variables so that each quantifier has a unique variable. That is, the same variable is not quantified more than once within the same sentence. For example, in the case shown here, we rename the variable x in the second disjunct to y. In the fourth step, existentials out, we eliminate all existential quantifiers. Now, the methods for doing this is a little complicated, and there are two cases. If an existentially quantified sentence does not contain any free variables and does not occur within the scope of a universal quantifier, we simply drop the existential quantifier and replace all occurrences of the quantified variable by a new object constant, that is, one that's not part of the language. The constant used to replace the existential variable in this case is called a Skolem constant. In the example shown here, we've replaced x by a, and the assumption a was not in the original language. If an existentially quantified sentence contains free variables, or if it lies within the scope of any universal quantifiers, there's the possibility that the value of the existential variable depends on the values of the associated universal variables. Consequently, we cannot replace the existential variables with a single constant. Instead, the general rule is to drop the existential quantifier and to replace the associated variable by a term formed from a new function symbol applied to the variables associated with the free variables, and universally quantify variables in the target. Any function defined in this way is called a Skolem function. So the example here illustrates the transformation. It assumes f is not part of the language. In the case shown here, the existentially quantified sentence contains a universally quantified variable x and a free variable y. And so we create a term by taking f and applying it to x and y. In the fifth step, all's out, we drop all universal quantifiers. Because the remaining variables at this point are all universally quantified, this does not introduce any ambiguities. In the sixth step, disjunctions in, we put the expression into conjunctive normal form, that is a conjunction of disjunctions of literals. It's accomplished by repeated use of the distribution rules listed here, same as in propositional logic. And in the seventh and final step, operators out, we eliminate operators by separating any conjunctions into its conjuncts and writing each disjunction as a separate clause. Okay, that's it for the general procedure. Now, as an example of this conversion process, consider the problem of transforming the expression shown here to clausal form. The initial expression appears on the top line, and the expressions on the labeled lines below it are the results of the corresponding steps of the conversion procedure. On the I step, we get rid of the implication operator. The N step has no effect since the only negation in the sentence is already applied to an atomic sentence. The S step has no effect because there are no duplicate variables. On the E step, we notice that the quantified sentence contains no free variable, so we simply replace the quantified variable by a new constant, in this case Greg. The A step and the D step have no effect. And finally, on the O step, we convert our conjunction into two separate clauses. Okay, here's another example. In this case, starting sentence is almost the same. The only difference is the leading not operator. But the result looks quite different. As before, on the I step, we get rid of the implication operator. This time, the N step's a little more interesting. We need to push that negation sign down through all of the sub-expressions. First, distribute over the existential, flipping it to a universal and negating the target. We then distribute the negation over the conjunction, leading to a disjunction of negated disjuncts. We distribute the negation in the second disjunct over the universal quantifier, flipping it to an existential and negating the target. We distribute that negation over the disjunction, and finally we eliminate the double negation. The S step here has no effect. On the E step, we note that the existentially quantified sentence does contain a free variable, so we replace the existentially quantified variable, in this case with a term consisting of a Skolem function and the free variable y. On the A step, we drop the universal quantifier. On the D step, we distribute the disjunction over the conjunction. And finally, in the O step, we convert our conjunction of disjunctions to two separate clauses. In propositional logic, the clausal set corresponding to any sentence is logically equivalent to that sentence. In Hebron logic, this is not necessarily the case. For example, the clausal form of the sentence, there exists an x, p of x, is something like p of a. This is not logically equivalent. It's not even in the same language. Since the clause exists in a language with an additional object constant, there are truth assignments that satisfy the sentence but not the clause. On the other hand, the clause is effectively equivalent to the original sentence in the sense that it's satisfiable in the expanded language if and only if the original sentence is satisfiable in the original language. And as we'll see, in resolution, this equivalence of satisfiability is really all we need.